Good evening. Tonight we are going to discuss 3.5 related rates in active calculus. In problems where two or more quantities can be related to one another and all the variables involved can be viewed as implicit functions of time t, we are often interested in how the rates of change of the individual quantities with respect to time are themselves related. We call these problems related rates. These problems often involve identifying one or more key underlying geometric relationships to relate the variables involved. Once we have an equation establishing the fundamental relationship among variables, we differentiate implicitly with respect to time to find connections among the rates of change. Here is a list of steps that could help you with determining these problems. First, we need to draw a picture. Then we need to identify what quantity we are looking for. After this, we identify the given information of the rates d variable over dt can be identified by changing, increasing, or decreasing. If the rate is decreasing, make sure the quantity is negative. Identify the equation that relates to the variable, then take the derivative to the equations with respect to t. Then we substitute any of the given rates given to us back into the derivative equation and then solve for the desired quantity. This isn't the step listed here, but we also need to finish with a sentence, and please don't put in changing because that will really make your professors upset. Here is an example that I have started so far and will work with you through it to get the answer. In this example, when a circular shield of bronze is heated over a fire, its radius increases at a rate of 1/5 centimeter per second. At what rate was the shield's area increasing when the radius is 50 centimeters? First, we need to draw a picture. I inserted this clip from Google. It's just a circle with a radius bar, and we know that our radius is 50 centimeters. But first, we need to identify what we are trying to find in our problem. So we need to identify what quantity we are looking for. And in this equation, we are looking for area, so that we know that we are looking for dA over dt. Because we are looking for the rate at which the area is increasing. Pardon my spelling mistakes. Now we need to identify what the equation has already given us. What the problem, I guess, is a better word. The problem has given. Again, with the spelling mistakes. So in this equation, it gives us a radius of 50 centimeters. So we know that r equals 50 centimeters. We are also given the 1/5 centimeters per squared, and that is our dr over dt equals 1/5. We don't need to necessarily put in the units now, just remember that they're there and they have to be in your final answer. So now that we have decided what we are identifying, now we need to figure out an equation. Because we are dealing with a circle and its area, we know that our equation is A equals pi r squared. Now that we have the equation, now we can take the derivative with respect to t. So your equation will look like dA over dt equals 2 pi r, since we took the derivative, times dr over dt. Make sure you take it with the chain rule with the dr over dt. It's just like the chain rule. And if you need help with the chain rule, look back on a different video. Now that we have our derivative, we can plug in the 50 and the 1/5 into r and into dr over dt. So then your equation will look like dA over dt equals 2 times pi times 50 times 1 over 5. And now we can solve for that, and that should equal dA over dt should equal 20 centimeters per second. Oh, 20 pi. I'm sorry, I forgot my pi. 20 pi centimeters per second. This is the answer to your equation, and see, I did include my units. That's a good thing. Now we need to end with a sentence. This is the most important part because it tells your teacher if you know what you are doing or not. So, the shield's area is increasing at a rate of 20 centimeters per second when the radius is 50 centimeters. Thank you for listening.